This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
In this lecture, we're going to go through chapter 5 of the free lecture notes for paper P2 and its learning curves. And let me talk for a few minutes about what learning curves are, what we're referring to. Just suppose I asked you this afternoon to make a desk. You've never made a desk before in your life, and so if all I did was give you some wood and said build a desk, maybe it'll take you all day to make it. But if I then asked you to make a second desk, I think the chances are that you'd be faster on the second desk, a third desk, a fourth desk. The more times you do it, the better you get at it. You're likely to go faster and faster and faster. And by the time you've made 100 desks, first one again may have taken you all day, but by the time you've made 100, maybe you can make a desk in 1 hour. Now that's what we're talking about, that it relates to labour, and that the more you repeat something, the faster you're likely to get. And it's very relevant for things like budgeting, because, you know, if I'm launching a new product and I know we're going to be producing thousands a year, then okay, I may make one unit first to sort of cost it out, but it's no good saying, you've made one desk and it took you 12 hours to make it, and therefore do my costings on the basis of 12 hours per desk, because we're going to be making thousands a year. And we know full well the first few desks will take a long time, but by the time you're making thousands, if you can make them in 1 hour each desk, we should be using 1 hour in our costings, not 12 hours just because the first one took you so long. So that's it, and I'll shortly show you how the numbers work, how we can sort of predict how much faster we'll be. But on the second page it says what we're going to do will only hold if the following conditions apply. It must be labour intensive. It's labour that's going to get faster. It must be a new product. You know, if I'm already making thousands of a particular product, then presumably the learning's already taken place. We're already going fast enough. So it's when it's a new product. First unit will take a long time, second unit will be faster, it will get faster and faster. It must be relatively complex. All I mean there is a desk is likely to take you a long time to make because it's quite involved. If it was something really simple, like just putting the end on a pen or something, you're likely to be fast enough anyway. It's unlikely that you're going to get much faster just by keep repeating. It should be repetitive. So, you know, it's where you're mass producing something, and so it's the same thing that you're making each time. There must not be extensive breaks in production. If for any reason, you know, you produce a few, then there's a long break. The danger is that you sort of start to forget how to make a desk, and when you start again, you start taking longer. And the workforce needs to be motivated, consistent, and important, experience little turnover. It says during the learning phase, in fact, all the way through, because you see, if you're my worker and you've gone through this learning phase and got faster and faster, fine. But if you leave and somebody else comes in, they're going to have to start learning all over again. You know, and it'll take a long time initially, then get faster. So I've already answered exercise 1. I've told you why. It says why each assumption is key. I've told you why in what we just chatted about. As to how it works, well, it's Wright's law. And it's stated at the bottom of the second page. It says, as cumulative output doubles, the cumulative average time per unit decreases by a constant percentage. Now we can read that 20 times and not really get anywhere. Let me show you exactly how it works. If you turn over to exercise 2, it says the first unit of output of a new product requires 100 hours. You know, it's a new product, we've made one, and it took you 100 hours. We're told that an 80% learning curve or learning rate applies to this workforce. Now, we'll talk later about where that figure may have come from, but as you'll see, that 80% is the speed of learning here, and in this question we're given it. It could be 90%, 80%, 70%, it could be anything. And it says, using a tabular approach, find the average production time per unit once the workers have produced 8 of these products. Now, see how it works. The number of units. So far we've made 1 unit. Jumping a column, I'll head up the columns the same there. It's got average time per unit and total time. That first unit, it told us, took us 100 hours. So that may seem a bit silly here. If 1 unit takes me 100, the average time per unit for that one unit is obviously 100. However, the learning curve rule says that if we double production, so we've made 1, if we now double it to 2, so we've made 1 extra unit, the average time per unit will fall to a fixed percentage of what it was before. Now, because the learning rate here is 80%, the average time was 100 per unit. Double to 2 units, the average time per unit will be 80% of 100, it'll be 80. Now, that's the average time per unit if we make 2. And so the total time, if 2 units on average take 80, the total time for 2 units will be 160. And so, here it says incremental time, the extra time. The first unit obviously took us 100. If we make 2 units, then in total they'll take 160 hours. So, if the total goes at 160, the time for the second unit is the difference of 60. So we're going to carry on, but this learning rule doesn't give you directly the time for the second unit. The learning rule gives you the average time per unit if we make 2. If we know the average time, we can work out the total time for 2 units. And again, if 2 units took 160 and the first unit took 100, the time for the second unit, the second unit is 60. So the first unit took 100, the second unit took 60. Let's carry on. Wright's law says that every time we double, the average time will fall. So if we double 2 up to 4, so we've made another 2 units. Each unit gets faster and faster and faster, but the average time per unit will be 80% of what it was before. Well, 80% of 80 is 64. And remember, that's not the time for any one unit. That's the average time per unit if we make 4. So the total time will be 4 times 64. 4 times 64 is 256 hours. Well, we already knew the time for 160 units, for 80 units was 100. The time for 2 units was 160 hours. The time for 4 units is 256. So how long did those second 2 units take? 256 minus 160 is 96. Well, that's the time for the third plus the fourth unit. And do note that one problem with the doubling rule itself is that it doesn't tell us how long number 3, number 4 will take. All I know is that 3 plus 4 together will take a total of 96 hours. But it may be, you see, maybe number 3 took 50 hours and number 4 took 46 hours. They're getting faster, but the doubling rule won't tell you the time for, again, the third or the fourth. Anyway, let's double one more time. If we double again, it goes to 8. So that's an extra 4 units. Each of those 8 units is getting faster and faster and faster. But the average time per unit, if we make 8, is 80% of what it was before. 80% of 64 is 51.2. And if on average each unit takes 51.2 hours, the total time for 8 will be 8 times that, which is 409.6 hours. And therefore, the total time for numbers 5, 6, 7 and 8, the first 4 took 96, the first 8 take 409. The difference, the total time for those last 4, I think is 313.6. Now I'm not going to carry on, but I think you see what's happening. Every time we double, the average time per unit falls by that fixed percentage. And there we are. But I've already said what the big problem is with the doubling rule. That although we knew the time for the first, although I do know the time for the second, I don't know individually the time for number 3, number 4, number 5, number 6, number 7, number 8. Third and fourth in total take 96 hours. The final 4 in total take 313.6 hours. Which is why there is later a formula which we'll look at, which will allow us to get individual units. But you still need to be able to use this doubling rule. Look at example number 3. It's very similar, but it says the time taken to produce the first unit is 100 hours. There's a learning rate of 75%. And it wants to know how long will it take to produce 7 more units. Well, you can never get the time of any number of units directly. All we can do, the way we have to do it, is we need to work out the total time to make 8 units. If I can work out the total time for 8 units, we already know the time for the first unit. The question tells us the first unit takes us 100 hours again. Well, if I know how long it takes to make 8 units, if I know how long it takes to make the first one, if we subtract, it'll tell us the time for the next 7 units. So we're always going to have, as you see in the later example, we're always going to have to take that approach. We can't get the next 7 directly. Work out the time for the first 8, take off the time for the first, and we're left with the next 7. How can I work out the time for 8? Well, fortunately, it's doubling. 1 doubles to 2, doubles to 4, doubles to 8. And so the time for 8 will be 8 times the average time per unit. And because it's doubling, we can work out the average time per unit. So a little bit of workings here. How long did the first unit take? 100 hours. What's the average time per unit if we make 2? The learning rate 75%, so 75% of that is 75 hours. What happens if we make 4? Again, it's 75%, which is 56.25. And what happens if we make 8? Well, again, 75% of the previous average. 42.1875. Now again, that isn't the time for any one unit. First took 100, by the time we've made 8, it may only be taking 2 hours or something. But the average time per unit, if we make 8, is 42.1875. And now we've got it. Because what's the total time to make 8? It's 8 times the average. So the total time for 8 times 42.1875 is 337.5. And now we're back to how I started. To make 1 took 100, to make 8 in total takes 337.5, and so the next 7 must have been taking in total the difference of 237.5 hours. So there you are. There is the doubling rule. It's hard, I think it's quite nice. Over the page you can see there's a graph there which I'm not going to try and draw on the screen. But you can see, I hope it was already clear how it's working. As you make more and more units along the bottom, the average time per unit on the vertical axis is falling. But you probably already realise from what we've been doing that although the average time per unit will fall, it goes like that, this sort of curve. Although in theory it'll carry on falling forever, you do get to the stage where it's going to be so infinitesimally small that effectively you get to a steady time. You know, they're not going to go faster forever. And we don't know when it'll be. I mean, maybe once they're making 100, they're going as fast as they possibly can. But there will come a time when you get to a steady state, when you're not going to go any faster. Anyway, that was the doubling rule. And I've already said you do need to be happy with the doubling rule. But it is rather limited. That last question wanted the time for the next 7. No problem, because fortunately, having made 1 and making another 7 takes you up to 8, and that was doubling. We can use the rule. But what if I'd asked you for the time for the next 5? The next 5 would have meant making 6 in total, and of course 6 doesn't involve doubling. And so if it's not doubling, then we have a formula, and it's on the next page. And as it's there, are you afraid you need to learn it? But that formula, y equals ax to the power b, y is the average time per unit, which so far we've been getting by doubling. A is the time for the first unit, x is the number of units, and b has its own little formula, the learning factor. B is the log of r over the log of 2, where r is the learning rate. And obviously you must have a scientific calculator, in which case you will have a log button. As to how we use it, well, I'll show you in exercise 4, but again, as it's typed just above it, When you're happy how to use the formula, go back and do the previous 2 exercises using the formula and check you get the same answer as you did by doubling. Maybe slightly different because of rounding. But if it is doubling, don't waste time. Double it as we did. If it isn't, then use the formula. So let's go through. Exercise 4. Flogel has just produced the first full batch of a new product, taking 200 hours. And Flogel has a learning curve effect of 85%. A. How long will it take to produce the next 15 batches? Well, despite me mentioning the formula, which we could use, for part A, if we've made 1 batch and we make another 15, we'll be making 16 in total. And so, as I was explaining before, the only way we can do it is to get the total time for 16 if we then subtract the time for the first, which we know it's 200 hours, then we'll have what we want, the time for the next 15. Now again, we could use the formula here, but I'm not going to, because 16 does involve doubling. 2, 4, 8, 16. And so if it does, it's quicker. Use the doubling rule. It's your choice, but still. And in fact, if you've understood me, it might be an idea to just pause this lecture and have a go yourself, and then press play again and check you got it right. So if you're going to pause now. I'll assume you did and you've restarted, so I'll do what you can check. Total time for 16. Learning rule only gives us the average time. So the total time will be 16 times the average time. And because it's doubling, as I said, we can get the average time. A little workings. The first tick's 200. Double to 2, and it'll be 85% of that, which is 170. Double to 4, 85% of that, which will be 144.5. Double again to 8. Again, 85% of the previous average. 122.825. Double again to 16. 85% of the previous average is 104.40125. Now, normally I would round. I haven't got to so many decimal places, but I may as well do here. But I'm not worried about a little bit of rounding. So the average time per unit, if you make 16 or per batch, is 104.40125. And so the total time, 16 times the average, is 1670.42 hours. And now, just like the previous example, we've got it. First one is 200, the first 16 is 1670. The time, therefore, for those next 15 is the difference of 1470.42. So, although I mentioned the formula, for part A, we didn't need it. However, look at part B. It's the same question, but it says, Flogel expects that after the 30th has been produced, the learning effect will cease. So I hinted at this before, that we're going faster and faster and faster, but once we've made number 30, we've decided we're not going to go any faster at all. So if number 30 took, I'm inventing the figure, if number 30 took 2 hours, from then on, they're all going to take 2 hours. And they want to know what time per batch should be budgeted. And again, I said at the very beginning, if in the long term they're going to take 2 hours, we should, in our cost card, budget on 2 hours a unit. Just because the earlier ones took longer is sort of a bit like a development cost. So I need to know, how long will number 30 take? Now, we cannot get that directly. All we can do is take the same approach as we did before. If I can work out the total time to make 30, and subtract from that how long it would have taken the total time for 29, then we'll have what we're after. So I'll leave a bit of a blank for some workings. And how long 29 take and how long 30 take, the difference will be the time for number 30, the 30th. And that's what we're after. Because I said a minute ago, if number 30 takes 2 hours, then from then on, they're all going to take 2 hours. So that's what we're going to do. Total time for 30 will be 30 times the average time per unit, as always. But this time, of course, we can't use the doubling rule. Doubling only works for 2, 4, 8, 16, 32, 64. We can't use the doubling rule. So we're going to have to use the formula. Now we're doing 30. Well, the average time per unit is y, which is ax to the power b. But before I can actually use the formula, we need to work out b. And b is the log of r, the learning rate, over the log of 2. Now the learning rate here is 85%, or 0.85. And although you should be able to, use your memory and use brackets and things, use your calculator efficiently, just so you can check, I'll write it all down properly. 0.85 log is minus 0.070581 divided by 2 log 0.30103, which if you divide gives 0.070581 divided by 0.30103. I get minus 0.2345. And usually, unless you're given a figure for b, usually write it to 4 decimal places. Terribly importantly here, b will always be negative, and it's going to make a big difference in a minute. It'll be negative, I don't know how much you remember from school or wherever, but because the learning rate is always going to be less than 1, it's 0.9, 0.8, or here 0.85, the log of a number less than 1 is always negative, but b is minus 0.2345. And so, still on 30, the average time per unit, or y, a is the time for the first unit, which was 200 hours. X is the number of units, or here it's batches, same thing. We're doing 30 to the power minus 0.2345. Now again, make sure you can use your calculator efficiently. Again, unless you've got a most remarkable brain, you're going to have to do that power in your calculator. Calculators differ, it depends what logic the calculator uses. So do make sure you can get this right. And although if you're efficient with your calculator, you can put the whole thing in, just so you can check it's 200 times. Well, I'll tell you how I get. I say it depends on your calculator, but I'll tell you how my calculator gets this bit. I go 30, well, I'll write it down, 30. I have a button, x to the power y, so I go 30, I press the button, x to the power y, oh shit, sorry, and then I put 0.2345, but the moment it's positive, but I then have a plus minus button to make it negative. I press that, and then I press equals, and I get 0.450417. Now I say, depending on which logic your calculator uses, yours may be different buttons, so be careful. But the trouble is, you see, the reason I've typed 0.2345 and then use the plus minus button to make it negative, if you type in minus 0.2345, then on my calculator, that supersedes the x to the power y. And I end up with 30 minus 0.2345, which is obviously ridiculous. So anyway, I'm sorry. You have to practice. If you have to have a problem, obviously look at the manual that goes with your calculator. But it does mean the average time per unit, if I multiply that by 200, it's 90 point, I'll just do it in 2 decimal places, 90.08. Now that's the average time if we make 30. So the total time for 30 is 30 times 9.08. 2702.4. I now need the time, total time for 29. So same idea, 29 times the average time per unit. But of course the new average time will be a bit different. So I'll use the formula again, this time for 29. The average time, the time for the first, times the number of batches, 29, to the power b. Well, once you've got b, it's the same all the way through, minus 0.2345. Which again, just so you can check, I'll write down in full. 29 to the power 0.2345 negative equals 0.454012. Multiplied by 200, it gives me 90.80. There's the average time per batch if we make 29. And so the total time, 29 times the average. $2633.2. And before I finish it, see, it is making sense. On average, when I made 29, remember, first one took 200, they're getting faster, 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 but on average, they're taking 90.8. If I make 30, well, number 30 is a little bit faster as well, so the average is just slightly lower. And how long did number 30 take? The difference between the two I shouldn't have done that in my head, but I think it's right. 2702.4 minus 2633.2. Yeah, number 30 took 69.2 hours. And the relevance, the question said that from the 31st onwards, they all take the same time as batch number 30. And therefore, you know, if we're going to have a big production, we're making thousands of batches a year, it's 69.2 hours that we'd bring into our costings. All right, two final things. One's on the next page and it's numbers. Throughout all those questions, whether it was the doubling rule or using the formula, for all of the questions, we were given the learning rate. It was 75%, it was 85%, and so on. And obviously, if you're given it, you use it. I've been through it. But in real life, of course, how would you know how fast they're going to learn? You know, I'm going to make desks. I've never made desks before. It's a new product. I can find how long it takes to make one desk. No problem. But how do I know the speed of learning? Well, the answer is quite simple. Make a second desk. Surely, if we make a second desk, we expect to go faster, we can work backwards. Before we look at example 5, just have a go at this. Suppose I tell you the first unit took 84 hours. I then got my people to make a second unit. And as you'd expect, the second unit is faster. The second unit takes 60 hours. Again, I beg you, pause this lecture for a second and just have a go at calculating for me what you think the learning rate is. If you're watching me, then you shouldn't be. Pause it and have a go. To the nearest percent. To the nearest percent. All right, I hope you have had a go, because only then will you realise the mistakes people can make. If you got 71%, you're wrong. I think, and I'm about to check, I think it's actually 86%. Remember, learning works on the average time per unit. The first unit took 84, no problem. If we double to 2 units, what will be the average time per unit if we make 2? The first took 84, the second took 60, and so on average, 84 plus 60 over 2, the average time falls to 72 hours. And it's the average time per unit that falls by this fixed percentage. And so you should have got a learning rate. If that was 74, or 72 rather, from 84. I think that's what I said before, yes, 86%. It's actually 85.7%, but I did ask for it to the nearest percent. So check you're happy there. It's surprising how many people learn what we did in the previous examples and can get that right. But then on this sort of thing where you're working backwards, where obviously the arithmetic itself is very quick, but it's so easy to be silly. You know, most people take 60 over 84, and that's wrong. Same idea, but they can make it a bit more fun. Look at example 5, exercise 5. Exactly the same idea, but it's related to the first 16 batches. It says number 1 took 100 hours. Number 16 takes 55.36. Well, we'll do exactly what we did before, but it's based on the average time per unit or per batch. And so if we make 16, the average will be 655.36 over 16. which is 40.96. Now, if the learning rate is R, then remember, we multiply by R each time we double. How many times will we have doubled here? We doubled once up to 2, 4, 6. It's late in the day. We doubled once up to 2, 4, 8, 16. We've doubled 4 times. And so R, start again, 100 times R to the power 4 is 40.96. R to the power 4 is 40.96 over 100. And therefore R is the 4th root of 0.496, which is, either use an nth root button or square root twice, 0.496 root. I get 0.839, or 83.9%, or nearest time at 84%. So don't get caught out by one of those. Finally, something that isn't mentioned in the notes, it doesn't involve calculations, but just think about this one. Suppose I tell you the workers in one factory, there's a learning rate of 90%. The workers in another factory have a learning rate of 80%. Which factory are they learning faster, A or B? Again, make sure you don't fall into a silly trap. It's tempting to say, usually with percentages, the higher the percent, the better. Ooh, A are the faster learners. In fact, B are learning faster. You'd rather, the lower the learning rate, the better. Think about it. You see, if the learning rate was 100%, the average would always be 100% of what it was before. They'd never get any faster at all. The lower the learning rate, the faster they're getting. Okay, well, as I mentioned in one of the earlier lectures, there are online practice tests for each chapter from the main CIMA P1 page. So go and have a go at 3 or 4 questions. Check you can get it.